I'm Dr. Matthew Richardson, and unfortunately, my co-host is not here with me, Joe. Um, he's currently ill right now, but he should be getting better soon, hopefully, and will be back with us next week. But yeah, today, guys, we're gonna be finishing up our conversations talking about the solar system, and we're gonna be talking about today specifically about planetary motion. Um, I'm gonna quickly look at the chat and see if you guys can actually see me. All right, what's up in ring? Oh, Peter. All right, here we go, guys. The volume's low. Yeah, I have a new mic here. I'm gonna see if I can move it a little bit closer. Is that better? I'm gonna move it a little bit closer to me and see if that may make a difference. Needs more? Huh. Let's just do this. Is this better? Can you guys hear me a little bit better now? All right. We can hear you fine. Just turn up the audio, but no change from you. Okay, that's not good. So I will admit that I am using my second Mac. My other computer had some issues, so I've had to change over everything to another Mac, and some of my settings aren't the best right now. Very quiet. Oh man. Let's just do this. Let me go into system preferences and see if I can boost the sound. And if that doesn't work, I'm just gonna hold the mic up directly. I'm going to try doing this. Can you hear me better? No? I'm waiting for system preferences to load up. In a few seconds, I'm going to end up holding my mic as if it was an actual like microphone, like right here in front of my mouth. Yeah, let me see if I switch over to my computer's. All right, let's do this. I'm going to switch the source of the sound. That's audio. Let's see what we can do here. Let's just use the built-in microphone. Is this better? Can you guys hear me a little bit better now? Yeah, my settings show that everything's turned up to the max. It's the same. All right. This is not good. This isn't the way I wanted to start the stream. Um it's a bit louder. Huh. Built-in microphone. The CM Tech is having the same issues. Hmm. Okay. I'm going to continue and I'm just going to try to talk louder and hopefully that like fixes things for me. Yeah, I think this might be a situation with OBS's settings for this computer, which I hadn't had enough time to actually make the changes that I want. All right, so you guys can hear me. All right, we're gonna continue, and hopefully, there's no issues with audio. All right, so today we're talking about planetary motion, guys. And so what I'm kind of showing right here in this image is actually the motion of Mars as seen from the perspective of Earth over the course of a little bit of underneath a year. This particular motion is known as retrograde motion, which is the idea that the apparent motion of Mars's movement in the night sky over time is such that it looks like it goes in one direction, then goes back in the opposite direction, and then goes back again in the direction it was in initially. This, of course, is due to the fact that the planets themselves have different um, orientations relative to the sun, and we're basically it's not really the true motion of Mars; it's an apparent motion. Um, but the main thing we want to get into is, well, what causes these the motions of the planets? Yeah, this is a composite image taken by an astrophotographer. I found it on a NASA site, and I unfortunately cannot remember the photographer's name. But yeah, it's a really cool image though. I agree with you, Finring. And so we're going to be talking more about what causes the motion that we see in the night sky of the planets. And to kind of summarize it, I mean, of course, it's primarily related to, of course, Kepler's laws of planetary motion. So, moving on from there, I'm pretty sure at one point in our lives we've probably seen an image of a sun in the center of some image, and then some circular rings around the sun that would correspond to the orbits of our planet. Now, we've grown up, of course, and we know that the orbits of the planets are not exactly circular, right? They exhibit a property known as eccentricity. They're eccentric, meaning that their orbits aren't perfectly circular. So, to give an example of what I mean by that, is here. So eccentricity is actually a quantitative value of exactly how circular the motion of an object is around some central point of rotation. So in this particular slide, I'm showing different values of eccentricity, starting from a value of 0. And as far as we're concerned, we can go up to a value of 1, where as you move away from a value of 0 for the eccentricity, you kind of get into more of an elliptical orbit. And so, with that said, of course, we need to understand, well, what are the key properties of an ellipse, right? So, as you can see here, of course, the circumference of the ellipse is oval. It looks ovular, if that's actually a word, but it looks elliptical. It's an ellipse, um, and it has a semi-major axis, which will correspond to the horizontal line in our image here, and it has a semi-minor axis, which corresponds to well, which would be equal to b times 2, where b is represented by the vertical line in the upper portion of the image. And then, of course, we have a radial value, r, that can be relative to one of the two focal points of our ellipse. In this case, we're just going to go with the focal point F and the radial value r, and you can kind of tell that as r changes in angle theta, its physical value will change. And of course, theta, of course, will change over time. But to kind of put this more into perspective and apply it to actual planetary motion, we come to Kepler's first law. Let me quickly make sure that I can actually see the comments as well, because I don't want to end up missing your comments. um, and so what we're kind of seeing here is essentially the exact same image we saw before with the ellipse, but actually being applied to, in this case, one planet being the Earth, depicted here by the bluish or cyan colored circle, and then an image of the sun, which would correspond to one of the focal points of our ellipse, depicted here by the yellow circle. And so Kepler's first law basically states that all planets um, orbit a star, in this case, our star being the sun, where the star will sit at one of the focal points. Um, and also a few other key things here. R plus R prime is equal to a constant. Um, that could be true, and I think that might be that's the definition of related to the definition of what the focal points are. It's been a while. I'm not too sure. I would have to. I think that's right though. I think r plus r prime is that's equal to a constant. Um, but basically, the key points that I want to note here is the fact that you can have 2 points of approach that are known as perihelion and aphelion. I always get that the word kind of mixed up there, which correspond respectively to points in the planet's orbit where it's either at the closest approach, perihelion, or at the farthest approach, which is aphelion. I know I always get that the word mixed up or messes up my ability to actually say the word, but those are the two important points within the orbit of a planet, and their physical distances can be determined like afar. Okay, so it's aphelion. Thank you, Hanny. So those two particular distances can be determined by the equations that are shown here, but I'm not going to go into that unless you want me to, but I'm not going to go into it. But this is Kepler's first law of planetary motion. But the thing about it is this, though. Kepler's first law isn't 100% right. And so let me go into why, well, what I mean by that. So, with that said, we need to go over to a different website or a different slide here, which is going to be a website. So just give me a quick second to bring that website up. There we go. All right. So this is actually a it's a simulator for stellar orbits, but nevertheless we can use it to kind of show the orbit of a planet relative to a star. So what I'm going to do is make a few changes to some of the parameters that we see in the upper left hand corner. Um, as far as the observational point within this image, it would correspond to like the little lighthouse or the little telescope house that's at the bottom of the screen. Imagine that you're in that house and you're looking up at this system, where in this case it's a two-body system, and you'd be looking at it edge on. Our perspective, of course, on the screen is going to be face on, but you'd be looking at it edge on, which corresponds to why you're getting the graphs you see in the bottom of the image here. So let me go ahead and pull that up, and I'm just going to make a few modifications to it to kind of make it seem more realistic to what the situation would be between a star and one of the planets that orbits it. So for mass 1, I'm going to reduce the mass, and we're going to imagine that this mass corresponds to the mass of a planet within the system. And for the second mass, M2, I'm going to increase it all the way up to, to the maximum value. Um, and the reason why it's important that I increase the mass of mass 2, in this case, a factor of 100 times more than mass 1, is because in reality, the masses of planets and their host stars are significantly different. For example, in our own solar system, Jupiter's mass is roughly like 1,000 times less than the mass of our star, the sun. So even with this particular simulation, we can't even this. Well, it will give us a good sense of what's physically going on in the system. So, and also what I'm going to do, just for visual purposes, I'm going to go ahead and reduce. No, I'm going to leave the eccentricity to that value, even though I could probably reduce it. Yeah, let's reduce it actually. Something that's a little bit smaller. There we go. So the orbit is closer to being circular, not quite circular. But nevertheless, we have our planet orbiting our star, which is kind of in the center there. And at the very bottom of the screen, we have two plots. One plot, the plot on the left, will be showing the radial velocity of our planet versus time, and the second plot on the right shows the radial velocity of the star over time. And the key thing you're seeing here, though, is that for the most part, this image kind of looks like the image I showed you before, where we have our star sitting at what would be kind of like one of the focal points of our ellipse here, and we have the planet going in an elliptical orbit. But the key thing I want to note here is that the star itself doesn't exactly stay still, right? If you look at the plot on the bottom right, you can kind of see these little wiggles. Um, and the wiggles become more apparent as I increase the mass of our planet, right? And the reason why this is important is because even though it may sit roughly at the focal point of our ellipse, truly what's actually happening here is that both the star and the planet orbit a common point. That point being the center of mass of the system. And so whenever in other words, what I'm trying to get at here is that whenever you think about Kepler's law, his first law at least, um, the star itself is very close to the focal point, but in reality, it's not exactly there. In fact, it orbits that point, or the center of mass of the system, along with the rest of the planets. And it's because of this reason that we're actually able to observe some of the exoplanets in our universe. A planet, of course, and I'm taking the case, of course, of a simplified case of a two-body problem where we just have our planet and the star. But the reason why we're able to see the star is by observing the light from the star and seeing how, or basically extracting from that light the radial velocity of the star, and noticing that the reason why it's able to do this wiggle in the sky or have a radial velocity change over time is due to the fact that there's a planet nearby it. And there's other things you can do with this simulator. That I'll go ahead and move the very last parameter here, which corresponds to the inclination of the orbital plane. So if you were to change the inclination, in this case, it's going to be edge on for us viewing the simulation. But for the person that's probably at the telescope, they're not going to see any sort of change in radial velocity at all because there's no line of sight velocity towards them as far as the motions are concerned of the system. But nevertheless, Kepler's first law is a very good approximation um, of planetary motion. And there's other things you have to take into consideration, of course. Like I said, this is a very simplified problem where we just have two bodies. But in the case of our solar system, we actually have, the sun and all the 8 planets and other astronomical objects in our solar system. And you have to take into consideration how those objects gravitationally influence the system as a whole. I'm quickly taking a moment to look at the questions here. So you're asking. So with the very last question there, Larry's asking, is the the Berry center being the center of mass, is it outside the sphere of the sun? Um, and I'm thinking like the solar disk, but I think that the center of mass of our system is for the most part inside within the it's encompassed within the sphere of the sun. Now I think I have seen um but yeah, I think it's very close to the sun center though. So could we use Doppler shift stuff like we use with exoplanets to find the planets in our own solar system? So the key thing I want to note about the Doppler shift is that the planets themselves don't produce their own light. Um, the light, as far as Doppler shifts are concerned, the Doppler shift that we're seeing is the Doppler shifting of the star itself. So we get the Doppler shift information from the star. However, and to get back to that Barry Center question, I have seen well, I don't want to say it's a plot, but yeah, I guess it's a plot of how the Barry Center changed over time, relative to the center of our sun. If I get the chance, I'll pull it up and we'll get a good look at it. But since we're talking about orbits, I wanted to take a moment to also be able to revisit a concept that we were talking about in the last stream that I completely got wrong. Um, and that concept was with the Lagrange points. So I believe in the last stream I stated that the Lagrange points correspond to um, points that are associated to two bodies, in which those points correspond to points of zero force, and that's not correct. Now the reason why I said that was because long ago when I learned the concept, I kind of made the wrong assumption about it, and that is that, and I'm going to go to my next slide here, and that is that these particular points, they correspond to points that if you place an object there that's of relatively low mass, you place an object there, and when I say relatively low mass relative to the two other objects that are influencing this particular third object that you're placing at one of the Lagrange points, um, it will have relative motion such that it doesn't change. It'll have constant relative motion. And I think a long time ago when I was learning the concept, I equated relative motion to a relative motion of zero, essentially, to a net force of zero, which is not right. But this will kind of show a video of what happens with Lagrange points. In this case, if we have, like, for example, the Sun and Earth system, and we have these 5 points, you could place an object there such that the object will maintain its relative position to the two more massive objects, but the net force on the object will not be zero, of course. Um, it can't be zero because it's actually in motion, right? It's in circular motion. Let me quickly. Well, no, I mean, yeah, Kepler was. You're right. Kepler was right for our solar system, and he didn't know about the exoplanets. But nevertheless, his laws are fairly accurate even for exoplanets. In this situation, wait, has it not updated? Oh my god, I've been talking here and I didn't properly. Thank you guys for. Let me get rid of the topic screen number two. I am so sorry. So I missed my chance to actually switch over or switch back to the slides. The very first image I showed was this image, which basically shows Lagrange points for the Earth Sun system. And then I wanted to be able to show what it looked like in motion. And basically, they correspond to positions where the relative motion between a Lagrange point and, in this case, the Sun and Earth, it will remain at the same relative position. But that doesn't necessarily mean that it's going to have a net force on it that's equal to zero. Thank you, Hanny, for pointing that out there. Is there any way to calculate the angular position of a planet in an orbit with eccentricity less than, or no, greater than zero, as a function of time without calculus? Um, I don't think I've. I think when I did the calculation some time ago, and I mean I've done it now a few times. I don't think I can't think of any way to be able to do the calculation without using calculus. If there is, by all means, someone post the link to it. So Hanny's asking, so do points one, two, and three in Earth? All right, all Earth all rotate at the same speed. Yeah, three, four, and five. Assuming a circular orbit, of course, should all rotate at the same orbital speed. So moving on, guys, to our next law of Kepler, the second law. This particular law corresponds to if you have of course a single planet orbiting its host star, excuse me. Um, if it sweeps, well, basically what this is saying is that a planet will sweep out equal area in equal time. That is, that if we could calculate the time it takes for the planet to sweep out the area that corresponds to the shaded region on the right hand side of our star here, that area would be equal to the area of the blue shaded region on the left hand side of the star, if and only if the orbital time taken to move from the intersections of the line between the star and the planet along those in this case, I'm trying to think of the best way of saying this though. The amount of time it's taken for the essentially the right triangle to be produced is going to be equal to the amount of time taken along the orbit, that is, for the left hand triangle to be produced. And that's essentially what Kepler's second law is stating. Now there is very simple math that you can apply to be able to get this to be able to calculate what the areas could be, to estimate what the areas could be though for this. No calculus is probably needed for this particular one, but for the to be able to be able to calculate the orbital motions, taking into consideration the eccentricity of the orbits, I think you need to be able to utilize calculus to do it. To calculate the areas, you can, and of course, you'd want to be able to assume that the amount of the change in the orbit is not going to be that much. So you want to be able to do the calculations using very small. Essentially, you want to approximate the areas as triangles. So what you can do is you can take the arc length times r. So what you'd want to do is you can take one of the lines between the sun and the planet, which in this case would correspond to a value of r at some instance in time, and you'd want to be able to multiply that by the amount of arc that the planet has swept out in some period of time. So r times that amount of arc that it sweeps out, where the arc itself, the arc length, is going to be equal to r times some change in theta, you can use this information along with the area of a triangle. So the area of a triangle is equal to 1/2 the base times the height. Where in this situation, the height of the triangle would correspond to the radial value r, and the base would correspond to the amount of arc length, because you're just gonna, if the arc is very small, you can basically approximate it as a line. So using that information, you can be able to calculate what the amount of area is being covered within some portion of the orbit. I'm pretty sure the calculation is somewhere online though. You could probably type in Kepler's second law and calculation, and it's not a bad calculation at all to be able to do. But yeah, moving on to our next slide though, which kind of which ultimately now covers Kepler's third law. Um, so basically, Kepler's third law relates the orbital period of of a planet to its physical distance between the planet and its host star. Specifically, the equation goes roughly as that the period squared is proportional to the semi-major axis of the orbit cubed. And so what I'm kind of showing here are a few of the well, not a few, but basically all of the orbital periods of the 8 planets, including Pluto. The 8 planets are our solar system and Pluto. So I figured it'd be really nice because I mean honestly I didn't know any of this information, except of course for Earth. I know Earth's orbit around the sun is equivalent to 1 year. Um, but I figured it'd be pretty cool to just be able to do a quick calculation of exactly whether or not these values live up to the law. And basically, the law states that p squared is proportional to r cubed, where p is the period and r is the value of the semi major axis. Now, it's easiest to use this equation in terms of units of years for the period and for astronomical units for the unit for the semi major axis distance. I missed Planet Nine. Well, at one point, Planet Nine. It's in there. Pluto's in there, but yeah, no longer a planet. Just give me a quick second. In fact, we'll go ahead and we'll use Pluto as our test case. So I'm going to quickly change some things up here. And I didn't really want to go too much into math, but I figured this will be a really fun little calculation to do. So if you give me just one quick second. Let's do this. And this can also probably give me a little bit of time to actually go back over some of the questions. So we have the periods, and so what we wanted to be able to do is calculate the the um the distance between the planet and the sun. So Pluto distance calculation. And so let's do this. I want to move this here. Typeset. I'm just going to send this to the desktop. So what I'm kind of doing right now is setting up some things so that we can be able to see the calculations. This kind of reminds me of the days when I would do a few calculations on screen. Let's see, here we go. Pluto distance. Oh wait, I don't want this one. Let's do the. Sorry, give me 1 second. Let's get rid of that one actually. I want the PDF. All right, this is better. All right. So we already know what the period is. Sorry, there's one more thing I have to set up here so that I can be able to actually show math equations. AMS math. All right. So we know that the period for Pluto is given here as 90,553 Earth days. All right. So we have to convert this value to units of years. So I'm going to typeset, and you guys can kind of see what I'm doing here. So 90,000. 553. All right. And this is in days. So, of course, in order to convert this to units of years, you divide it by, well, we're just going to round up to 365 days. And so you can see what I'm doing here. Of course, I'm going to have to use my very own by 365. This corresponds to 248, well, roughly 248 years. So in units of years, the dwarf planet now, Pluto, orbits in 248 years. Now, using Kepler's third law, which states that the period squared is proportional to the radius cubed. In this situation, though, I'm just going to basically say that the period squared is equal to the radius cubed, as long as we're working in units of years in AU. And I am sweating, yes. You guys can see that. My plan, of course, today was to wear my other CosmoQuest stuff. I had a t-shirt, but I couldn't find it. Let's see. So far, so good. And so, of course, to solve for the radius, we basically can state that the radius is going to be equal to the period to the 2/3 power. And that shit typeset. And so now what we're basically just going to do is just plug in the value that we have for the period in units of years and get the answer for the radius of the semi-major axis in units of AU. And what this should end up giving us, and I'm just going to go ahead and type this into my calculator here. So 248, this quantity raised to the 2/3 power. This should correspond to an approximate, this is approximately, of course, it's going to be an exact value. I've rounded some things here. But I get a value of roughly 39.5. And this is going to be in units of AU. And so, of course, we can verify if this is the case by just going online and finding a source for the information. Yeah, the hoodie feels great, but it's making me extremely hot right now. Yes, I'm sorry. Let me increase the font size. But this is putting one of Kepler's laws into action. Sorry for the formatting here because I'm trying to quickly get through it though. Probably can just indent. Now, the reason why I'm doing this too is because I haven't verified any of this information. The source where I got the plot from seemed reputable, so I figured, of course, they got the right values, but I haven't done any of the calculations beforehand. But 39.5 AU should be the period, or not the period, but should be the orbital separation between our star, the sun, and the dwarf planet Pluto. But if we were to go online, and so what I'm going to do now is switch back. Let's go back to the topic screen too, because this is already linked to online. What I'm going to do now is pull up another web page. Let's see what it looks like for you guys. All right, I'm going to have to move that probably. But I'm going to pull up another web page, and basically I'm just going to see exactly what the orbital separation is. So let's see if you guys can see this. I think you can. Yeah, that's good. And so basically online, it says the semi-major axis is 39.48 AU. And I think our calculation, and I did round it too, but I think we're kind of like spot on it for the calculation, which shows that Kepler's law works. And I mean, earlier Larry noted that the Kepler's law, of course, was taking into consideration the planets of our own solar system. However, you can actually go online. There's a few websites, and I can't remember the website that's coming to mind right now, but there is a website with a lot of Kepler data, and you can produce plots from the data, and one of the plots you can produce will basically show this relationship. That is, if you have the orbital period along the y-axis and the orbital separation or the semi-major axis separation along the x-axis, and you were to plot this in terms of I believe it has to be a log-log plot. Yeah, it would have to be a log-log plot. Um, but basically, what you'd end up getting is the relationship that I just showed here in the calculation. That is that the period squared is equal to the radius cubed, or the semi-major axis cubed. And so now what I'm going to do, that pretty much concludes the discussion, but I want to see if I can go back and catch some of the comments and questions that I missed from earlier. So, so Hanny did ask a question that I wanted to actually address. And when you asked the question, I was thinking about Kepler's third law actually. So you asked, so do the points one, two, three, and the Earth all rotate at the same speed? And someone already in DPI stated that three, four, and five do, and that's right. And the reason why this is right is because of Kepler's third law. In the case of points, let me go back to the let's do this. Where is that? It's here. Oh yes, here we go. I'm gonna go back and I'm gonna bring the screen back, and I'm going to go back to the drawing. All right. If you notice, and even better with this drawing, or not with this animation, if you notice, points 4, 5, and 3 and the Earth are all along the same orbital track. However, points 1 and 2 are along different orbital tracks. That is, they're in this situation they're physically closer to the sun or the star, or one is closer to the star and two is farther away. And so the amount of time it would take for those to for an object that's stationed at either points 1 and 2, it's either going to take a shorter amount of time, which would correspond to point 1, or it's going to take a longer amount of time, which corresponds to point 2, for it to orbit around the sun. But yeah, like DPI stated earlier, though, points 4, 5, and 3 in the Earth, given that they're all at the same orbital separation, will all orbit at the same with the same will orbit around the same time. Let's see. Let's get back to the questions. Do they use Kepler's laws for space missions? Um, I'd probably say that they probably that many of the simulations probably start with Kepler's laws as a base, um, as like the base for the calculations. But they probably, of course, make corrections to it. The GIF looks like a spinning record. But yeah, I mean, I would think that many simulations that that simulate the dynamics of objects in space um, would probably start off with, can probably be reduced to Kepler's laws under certain conditions, but would probably, of course, need, if you're starting off with Kepler's laws, you would need to be able to make corrections for other types of interactions. Like, for example, even with this, well, no, not with this, but yeah, yeah, with planetary orbits. For example, our system isn't just composed of just the sun and the Earth. It's the sun, the Earth, and all the other seven planets, and other astronomical objects. And those objects, as I stated earlier, will have gravitational influences on on, for example, the orbit of the Earth. And so you'd have to take that into consideration as well. And I'm pretty sure there's some other considerations too, but I can't think of them at the moment. Hey Ryan, what laws are the corrections from? I mean, gravitationally speaking, um, gravitationally speaking, the um, the planets, the planets, gravitationally speaking, other planets affect the orbits, or a planet can affect the orbit of another planet. I don't think it's so much to the point where it would I don't think it's so much to the point where it would perturb an orbit to the point where it'll cause it to be unstable, but I think it's more so that it can change, slightly make changes to the dynamics of the orbit over time. Yes, exactly. It's like other interactions have to be accounted for. And I'm pretty sure there was some more questions up above that I wait. Noel states here that Kepler's second law appears to use a derivative of a. Well, in my situation, I was talking about a simple approximation. If you want to be able to calculate what the area, so going back to that slide, if you wanted to be able to make a very estimate of the area of the shaded region, um, in the condition where the arc of the orbit is small, you can simply imagine that the base of our triangle isn't really an arc, but it's kind of like a straight line. And with that assumption, you can say that well, you know the arc length is going to be equal to it comes to be r theta, or in this case r d theta, because you're taking some small change in the orbit. And so you can make the approximation that that arc, which has a value of r d theta, is a straight line. And if you imagine that the arc is a straight line, you essentially have a triangle, and you can essentially apply the equation for the area of a triangle. Which, like you stated earlier, I mean, yeah, it's a derivative. It's a derivative, but I mean, the derivative itself, d theta is basically just saying some change in theta. That's what a derivative is. It's the change in one thing relative to the change in another thing. But the differential, though, the d theta itself is just basically a change. It's a difference. Okay. So Peter's asking what happens if you slingshot around the sun at light speed. Well, superluminous motion. I don't think that's not currently possible. Of course, um, moving faster than the speed of light. But and so this kind of gets into those other types of corrections that you'd have to take into account for, right? Um, and now you're getting into relativistic effects. So slingshotting. So, but now you have an interplay between the inertia of an object versus the gravitational influence on it. And so slingshotting around the sun, I don't think there would be much of a slingshot. I think if you're traveling at light speed or upwards, you're not going to slingshot. You're just going to zip past it. Now, if you're talking about more denser objects, that's different. Even if you're talking about like a black hole, um, if you're moving, if you were even able to move at the speed of light, once you pass the event horizon, you you wouldn't slingshot. You just you'd be going directly into the black hole. Yeah, exactly what Larry said there. Light speed by beyond. Yeah, you wouldn't slingshot. You zip right past it. Um, you leave the system in a hyperbolic orbit. Okay. All right. Well, the thing about it is that I mean, the gravitational effect. Are you talking about for the sun or for like a black hole or both? Hmm. So earlier when you guys said about the hyperbolic orbit, um, it's true, but for all essential purposes, though, if you're traveling at this, well, no, 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 no. Let me think about that actually. No, you guys are exactly right. But the shape of the hyperbolic orbit, though, I mean, over very short distances would probably look like a straight line almost. Yeah, Hannah, you're right. You wouldn't be captured. But for all essential purposes, if you're traveling at the speed of light and you pass by, even if you pass by really close to the sun, given its gravitational influence on you, your trajectory over small distances in the vicinity of the sun would look like a straight line. But if you were to kind of like zoom out, the line wouldn't look so straight. It would be slightly bent. You guys are giving me a lot of things to think about. These are things that I typically don't think about on a day to day basis. I love our conversations, guys. Hey, Miklos. All right, guys. I think I'm gonna cut the stream because I'm pretty sure that And I think I'm right. I think Astronomy Cast should be beginning very soon. All right, guys. Well, I will see you guys next week. Hopefully Joe will be back, and we should be starting a new discussion on another topic in astronomy. So I will see you guys then. All right, guys. Bye. Yeah, Peter, I should be there for Astronomy Cast. I'm typically there. I'm just like in the background, just listening to everything. Thanks, Susie. All right, guys. Bye.